my name is Justin Dehart, and this is my final project for our Introduction to Computational Fluid Dynamics course. CFD is a branch of fluid mechanics that uses computer simulations to analyze fluid behaviors around and within objects. In this project, I applied CFD to test the airflow over a Formula One front wing design. What is CFD? Computational Fluid Dynamics, or CFD, is a field within fluid mechanics that uses numerical simulations to analyze and solve problems involving fluid flows. Essentially, it's all about using computers to simulate how fluid like air or water behave in and around objects. CFD is built on the Navier-Stokes equation, which describes fluid motion by considering properties like velocity, pressure, and temperature. These equations are incredibly complex, so solving them by hand is almost impossible for real-world scenarios. That's where CFD software comes in. By leveraging computational power, we can predict how fluids interact with surfaces and optimize designs before physical testing even begins. For engineers, this means faster innovation and more efficient solutions. CFD is a versatile tool with applications across many industries. First, in aerospace and defense, it's used to design aircraft wings, optimize rocket nozzles, and study high-speed airflows like those around subsonic jets. In the automotive and motorsport industries, CFD helps improve aerodynamics, reduce drag, and increase downforce, which are critical for performance. It's also used to develop cooling systems for the engines and brakes. Biomedical engineering, CFD is applied to simulate blood flow in devices like stents and heart valves, and to optimize drug delivery systems such as aerosols for respiratory treatments. HVAC systems, CFD ensures efficient heating, ventilation, and cooling designs for buildings. Also in renewable energy, it's key for improving wind turbine efficiency and analyzing wave and tidal systems for sustainable power generation. No matter the industry, CFD provides critical insight that would otherwise be challenging or impossible to gather through physical testing alone. CFD is essential for modern engineering for several reasons. It allows us to improve designs by simulating real-world conditions. For example, in motorsports, we can model airflow around a Formula One front wing to optimize downforce and drag without needing physical wind tunnel tests for every iteration. CFD gives us detailed visualizations of fluid behavior that make it easier to identify problem areas like turbulence or pressure differences and develop targeted solutions. Physical prototypes and testings can be expensive and time-consuming. CFD lets us test virtually, accelerating the development process without cost repercussions. It also allows engineers to simulate extreme conditions such as supersonic flows or harsh environmental scenarios that might be unsafe or impractical to test physically. In high-stakes industries like Formula One, these advantages translate into better, faster, and more innovative designs that directly impact performance on the track. The focus of this project was to analyze the airflow over a Formula One front wing design. Aerodynamics play a crucial role in motorsports, and the front wing is one of the most crucial components for generating downforce and managing drag. My goal was to use CFD to simulate real-world conditions and evaluate how the wing performs under airflow. Specifically, I wanted to assess the pressure distribution and airflow characteristics which directly affect downforce and stability at high speeds. By understanding these factors, we can refine the design to improve overperformance on the track. To begin, I designed the Formula One front wing geometry in SOLIDWORKS. This involved importing the NACA 4412 wing into SOLIDWORKS, and using the different tools like copy, paste, rotate, and scale, I constructed this wing design. Once the design was finalized, I imported the geometry into ANSYS. Within ANSYS, I set up a flow domain around the wing using a C mesh structure, and then used the Boolean subtract feature to integrate the wing design into the C mesh structure. This domain represents the space where air interacts with the wing, providing the foundation for accurate simulations. By carefully defining geometry, I ensured the simulations would replicate real aerodynamic behaviors. Next came meshing, one of the most important steps in CFD. Meshing involves dividing the flow domain into smaller, discrete elements that the software uses to solve the equations of flow motion. For this project, I set the solver preference to fluid and the element size of 0.5 meters. I used triangular elements to create the mesh, as they are well suited for complex geometries like a Formula One wing. The mesh was refined by making the body element size 0.02 meters, along with the airfoil edge size to 0.002 meters. I specified smaller element sizes in these regions to capture the fine details of flow separation and reattachment. The simulation was set up as a transient using a K-epsilon turbulence model. Air was defined as the working fluid, and the inlet boundary conditions specified an X velocity of 102.78 meters per second, replicating race conditions. Residuals were monitored with a coverage threshold of 1e to the negative 6. Calculation features of the pressure and velocity contours were set for the number of steps at 1,000, the time step size at 0.01 seconds, and the iterations per step were set to 25. Velocity contour revealed how air moves under the wing surface, particularly under the bottom surface, which created downforce. The red is the faster high-speed air, where the blue is the low-speed air. As you can see, the trailing air comes out smoothly, which indicates good aerodynamics of the wing. Pressure contours provide clear evidence of high pressure zones on the underside and low pressure zones on the top, confirming the effectiveness of the wing in creating downforce while managing drag. In conclusion, the project demonstrates the capabilities of CFD in analyzing a Formula One front wing design. By simulating airflow and visualizing key aerodynamic factors, I was able to assess the wing's performance and validate its ability to generate downforce efficiently. This project underscores the importance of CFD in motorsports design, where even small improvements can lead to significant gains on the track. Thanks for watching, and don't forget to like and subscribe.